so my name is Stefan Puschnigg. I work for the Energy Institute in Linz in Austria. And yeah, I was invited to give a presentation about the project HY2HEAT, which we finished in April 2025. So to my background, I'm a mechanical engineer and I work already now for 7 years for the Energy Institute. So the project I'm talking about is called HY2HEAT, which basically means hydrogen to heat, and is focused on using the electrolysis waste heat for using it into district heating networks. So that was the aim of the project. As it is seen here, also on the next slide, the project was coordinated by my organization, and there were 3 other enterprises involved. That's our SINTEF, so with Hanne Kauko as the project manager. We had the AIT on board and also the Tallinn University of Technology. So actually SINTEF and AIT was also part of today's meeting, like at least some people. So you're quite aware of those organizations. Each partner had a specific topic or a specific task. So as the Energy Institute, we were leading the project and we were doing a bit of an analysis how in the future, the hydrogen framework is evolving. So it means what is expected of or which amounts of hydrogen capacity will exist in maybe 2030 and 2050. SINTEF was responsible for doing how can you technically integrate the waste heat from the electrolysis process into the district heating network. The AID was responsible for technical economic assessments, and the Tallinn University did a survey on what might be barriers or opportunities for all involved stakeholders that this waste heat is then used in the future. I have a bit of a background provided here. So as said, it's about using the electrolysis waste heat, and as you all might know, currently this hydrogen is produced from fossil resources, and if you think about a climate neutral energy system in the future, that will be there will be hydrogen as a key pillar, of course, and electrolysis. So the process of splitting water into hydrogen and oxygen might be one of a key technology, and therefore we expect that the production capacities will evolve on a global scale. But when you produce that hydrogen around 1/3, so it's an average number depending on the technology used, of course, but around 1/3 is wasted as heat, and that's exactly what we are targeting it within our project, that we want to make use out of that heat. And the project was funded by the IEA THC Annex 14. And if you want to find more information on that, I have provided here the link to the IEA THC website regarding our project number 6. So as said, the aim is of the project to assess the volumes and the expected capacity of electrolyzers in the future. How can we best integrate them, and what could be a guideline for district heating operators that we really can use that waste heat in the future. And the project was conducted because of several reasons. On the one hand, first we want to raise the awareness of the policymakers that we take already now the right steps, that we don't forget about that unused or mostly unused waste heat potential. We want to support the district heating operators, companies who invest in hydrogen production capacities, that we can show them already now that it might be from a technical economic side, but also from a poor technical side feasible that you integrate that into your systems. And it can also be a solution for future district heating networks which are running on lower temperatures, so that you can directly maybe integrate the waste heat from the electrolyzers into their district heating network. I have here provided a figure where you see in the center the electrolyzer, and you see all the blue arrows are then related to hydrogen flows. The red arrows are related to heat flows, and the yellow ones are related to electricity flows. And if you have here in the green colored rectangle, you see the HY2HEAT focus area. So we were analyzing, okay, you have the electrolyzer, you produce the hydrogen, but we are interested in the waste heat, and that can either be directly integrated into this district heating network or, for example, upgraded via heat pump. And then, of course, it somehow comes if you use that waste heat in the heat merit order, which is quite known in district heating systems, that it's of course a competing source against other conventional storages or future hydrogen supplied heat sources. And yeah, that's then used in the district heating network. And this, we call it 3 key dimensions, like hydrogen, electricity, and heat. Based on that 3 key dimensions, somehow, operational strategy needs to be developed. So depending on local characteristics, that might be differ. So for example, running the fullest hours of electrolyzers per year, for example, could one key fact or one key parameter, which then defines your operational strategy and how much waste heat you can expect. We started in the project in the beginning with an analysis for the IEA DHC member countries on what electrolyzers capacities do we have to expect for 2030. That's the figure on the left-hand side. Until 2050, that's the figure on the right-hand side. I don't want to go into detail into each country, but horizontally, it was the IEA DHC member countries with the expected capacities of electrolyzers capacities. And you see always like a dark colored bar, and then always on the top there's a lighter color bar, which means that there's always some range if you go into the roadmaps. So we analyze the roadmaps, the strategies, and try to get those numbers. And that we did for 2030. So there is a quite good picture already, since we found for every country data on what their plans are. If you take a look on the right hand side figure, you see the blue bars are related to 2050 values, where countries have stated specific targets or strategies. If there is still an orange or yellow colored bar, that means there are no specific values found, so there's no strategy until 2050 available. And yeah, in addition, we have analyzed from the European transmission operators, so from ENTSO-E and ENTSO-G, they have like this 10-year network development plan, and they made some simulation for a climate neutrality scenario of Europe. So therefore, only Europe countries are now considered, where they calculated the amount of electrolyzers capacities per country for a climate neutral Europe, and that are these green diamonds on that for each country. So which says, okay, if I by country have this target reached or not, which basically says something about how good is the progress of each country. And by this electrolyzers capacities, we calculated then the waste heat potential, assuming the full load hours. So we made the sensitivity analysis and calculated then, for comparison reasons, the electrolyzers waste heat per country, and we put that in per capita, so we have a comparison. And in total for the IEA DHC member countries, that's around 408 terawatt hours for 2050. So that's almost almost a European district heating demand. It's just for comparison reasons. But you can find all the details for each country regarding capacities, waste heat potential, sensitivity analysis that will be made available in our final report once it's approved. For the technical integration part, we had a case study in Norway, which is located in Bodo. There we had the district heating network with supply temperatures of 80 degrees and the return of 50 degrees. And there, the current district heating network is based on a biomass boiler for the base load, and there's an electric boiler also for peak demands. And there we analyzed the impact of an alkaline electrolyzers, which has a waste heat temperature of 55 degrees or 75 degrees. So it depends on the operation settings. So we analyzed both scenarios. And based on our technical integration we try to analyze 3 configuration options. So the first one is that you simply lift all the temperature which is available via heat pump to the required temperature of the district heating network. So only using the heat pump. A second configuration is that you preheat the return line before upgrading it with the heat pump to the temperature level. And the third configuration is that you preheat the return line after heat pump upgrading. So these 3 options were analyzed, and based on that, we made some simulations. That was the part of SynTF, so I just go over the complex details. So basically, you can say the higher the waste heat temperature, the better. That's kind of obvious in every case, but it lowers the higher the waste heat temperature is, it lowers the heat pump capacity. And as you see it here, it's 55 in case 1, and case 1 with 75 degrees, the capacity of the heat pump decreases. In addition, the coefficient of performance increases if we have higher waste heat temperatures. The essential message was within our analysis that the preheating makes the real difference when integrating the electrolyzer's waste heat. So if you preheat, you can reduce the heat pump capacity by 50%. So that's essential. And you can increase your COP by up to 110%. Yeah, so to see it here again, it's from 8 almost to 17. So that has a huge impact. So the best case is always to preheat that as it is shown here. But of course, the requirement is always that that you have at least a 10 grad Celsius difference in the temperature, so that you can really make use out of that. Then for the techno-economic analysis, the question was raised, okay, how much can the levelized cost of heat be reduced, or how much the levelized cost of hydrogen? And that was based on 3 case study in Bodo again, but also one in Austria, in Jenbach, and also one in Tallinn, in Estonia. And I just go over that compactly. So you have basically the hydrogen system, where you usually cool away the heat, like that you have like this constant operation temperature. And then this decision is, okay, should I use this waste heat in the district heating network where you have other competing temperatures systems? And yeah, if you compare then that for the levelized cost of heat, you see, for example, in Tallinn, the impact was rather low since the electrolyzer's heat was rather limited compared to the heat demand. But for Jenbach and for Bodo, the levelized cost of heat, if you compare it with and without waste heat integration, that can reach up to 27%. So the reason why it is so high for the Bodo case is that the ratio from electrolyzer's waste heat to the heat demand of the network is up to 30 degrees. So that's the reason why the impact is then also that high. And if you take a look at the levelized cost of hydrogen, you see that also the levelized cost of hydrogen can be reduced. But this also depends on the full load hours. So the higher the full load hours, the more waste heat is provided, and the higher the impact is done on the levelized cost of hydrogen. But of course here the electricity price, it's listed here for Tallinn. It was the average price was rather low, high with 91 euros per megawatt hour compared to Bodo with only 33. Yeah, and in the end of the, we also made a survey which were aiming to explore the key challenges and drivers of integrating that waste heat into the district heating system, with all the target groups who are relevant, with researchers, with district heating companies, electrolyzers, operators, policymakers. And we got 70 responses. You see here, sure, most of them were researchers, but nevertheless, we had 12% of, for example, district heating companies. And yeah, we collected all the answers from them. So we had 9 cases, which are listed here. And only one is currently connected electrolyzer is currently connected to the district heating network where the waste heat is used, and that's the case in Denmark. And regarding all the operational strategies, there was also always stated that some use it, for example, only to produce the hydrogen. Some use it, for example, to store it on a seasonal level. Some operate the electrolyzer if you only to use excess renewable energy. So that's quite flexible at the moment. And also from a technical point of view, that varies, since sometimes there's only minimal adjustments necessary and sometimes you have to adapt the full infrastructure. And also in terms of costs, that depends on the technical requirements and so on, operational strategy. And then we try to get that all the answers regarding challenges and to derive based on the challenges some policy recommendation. And as you can see here, like we structured them according to the type of stakeholder, but the main challenges were the high investment costs, that the electricity prices are fluctuating, issues regarding the proximity of district heating network and the electrolyzer location, and also all the regulatory aspects and legal barriers which are existing are quite relevant. And based on that analysis, we had this policy recommendations where, that's basically covering or summing up the introduced points before. That there is still research necessary. We need to foster collaborations. There needs to be some subsidies for infrastructure, and we have to encourage district heating operators to engage in hydrogen production and to really make aware of there's a waste heat potential available which can be used. I skipped the dissemination activities of the project, so we're but active here and that level. And to conclude, so waste heat can support the decarbonization of district heating network, but of course it depends on this operational strategies of the dimensions of heat, hydrogen, and electricity. Preheating makes the difference, so that's quite a good conclusion. And if you think about the stakeholders, so it's technically and economic feasible, but that's of course depending on the case study. So you have to look at that from case to case. And now it's time to make the stakeholders aware of use that waste heat potential in your district heating network. That's from my side everything. So feel free to ask or if you have further questions on that part.